So in the previous video, I went and defined the main 8 properties that we need in order to go and define and manipulate linear combinations. And then from there, we were able to go and investigate the span of a bunch of matrices and whether a bunch of matrices were linearly independent or dependent or not. So those problems are there to get you ready for doing the same thing in general. You really don't ask those questions very much at all, but it's important to see that you can do it. Unfortunately, though, the way we define matrix multiplication was so that we could support linear combinations in some kind of clever way. But because of that, a lot of the algebraic properties that we would like to be true are just not. So as an example, take these 2 matrices. If you go and multiply them together, notice that when you do so, that you get the matrix 3, 12, -1, and -4. Seeing that's true is not in any way difficult. See why? All you got to do is just take a certain row and multiply it to a certain column, and you'll wind up getting that entry right there. So it's not hard to see why it's true. But if you go take the matrix and multiply them in the different order, so take B times A, this time you then get that. You get the matrix 2, 6, -1, -3. You get, well, basically a whole different answer. So that's really bad. That's really terrible. That means in general that A times B does not equal B times A. It's actually worse than that, because not only the left-hand side, A times B might be a defined product, but B times A not only is it not always equal to A times B, but it may not even exist. The object itself might not exist because of the dimensions not lining up correctly. So that's really bad. Oh, but it gets worse than that. Oh, yes. Look at this one. Take A and square it. That means A times A. If you take A times A, you get the 0 matrix. What? How's that possible? Yeah, it's true. That's totally possible for matrices. Yeah, it's fine. So it actually says then that it's completely fine. You could take a matrix and square it and get the 0 matrix, and yet the matrix was not the 0 matrix in the beginning. That has other weird consequences. It means it's possible to take a product of 2 matrices, and yet when you multiply them together, neither is the 0 matrix. But when you multiply them together, you do get the 0 matrix. The consequence is that everything you've ever learned on how to solve polynomial equations, none of those techniques are going to work for matrices. If we ever have a polynomial matrix equation, you can't just say factor it, and then since the factor's product equals 0, that means one of the factors in that product must be 0, because that's not true. It's possible to get a bunch of matrices that are not 0, and yet their product is 0. And that means then all the normal techniques you guys learned for factoring and solving polynomial equations will not work with matrices. So here at least are some properties that are true. So if A, B, and C are matrices so that all these operations make sense, and C is any scalar, then the first property says, this is called the associativity property. First property says that the parentheses can be put in any order. You can put them anywhere you like, and the matrix multiplication in the end will be the same. So that means then that we're free then to just not write down parentheses. I can just write A times B times C, and it's totally fine, because where the parentheses would go wouldn't matter anyway. I can't change the order, though. I can't take A and B and swap them. I can't take B and C and swap them. I can't take A and C and swap them. That's all commutativity. That's not true in general. The next 2 properties, that's these guys. These are called the distribution properties. They allow you to take a matrix multiplication and distribute it through a matrix addition. But notice that you don't change the order of the symbols. So see how A here comes first and A comes first in these products. See here how C comes second in the product, and see how C comes second in the product. So the next one is just what you can do with scalars. If you have a scalar in a matrix product, you can just put the scalar up front. So then that makes it a lot easier not to worry about scalars. We just pull them out and put them out front of the product, not worry about it at all. The last 2 are that if you take a matrix and you multiply it to an identity matrix, that's these guys. That's a square M by M diagonal matrix where all the entries on the main diagonal are 1. And then this is a square N by N diagonal matrix where all the entries on the main diagonal are 1. If you ever take a matrix and multiply it by the correct size identity matrix, you just get the original matrix. So the identity matrix is just playing the role of 1 in multiplication. So all these properties here are, well, pretty important, but I'm going to prove only one of them. I'll just prove this guy right here. So let's go ahead and do that. It doesn't take too long to do so. Let's go ahead and prove that for any matrices A, B, and C, provided that A times B plus C is defined, then it always equals A times B plus B, A times C. To show you why, the very first thing you have to worry about is that since this is actually an equation about matrices, there's a matrix on the left of the side of the equation, there's a matrix on the right-hand side of the equation. To show those matrices are actually equal, I have to show at least that they're the same size. Then I have to show that corresponding entries are equal. Really quickly, I'll explain why that at least the left-hand side and the right-hand side have to be matrices of the same size. So on the left-hand side, if this thing is defined, then this B could be, let's say, N. It has to be like an N by R. This could be like an N by R. That way the addition is defined. And the A then would have to be like an M by N. Otherwise, the multiplication would make sense. This overall addition and product of things would be a M by R matrix when you're done. But then we know what A and B size is. So A times B would then have to be an M by R matrix. And again, we know A and C's size. I just wrote them down. So that would have to be an M by R matrix. And when you add them together, you get a M by R matrix. So yeah, that makes sense. Sure, that's fine. So at least these two matrices on the left and the right-hand side of this equation that are equal to, they're at least the same size. So now I will show that the corresponding entries are equal. That will then say that the matrices are equal. To do so, let's just use our normal notation that boldface capital letters with a subscript corresponds to a row of a matrix, while lowercase boldface vectors correspond to columns. So then that means then if I want to know the jth column of the matrix B plus C, I would find the jth column of B to find the jth column of C and then just add them together. So the jth column of B plus C is B sub J plus C sub J. Okay, with that in mind, I want to know then, what is the ith jth entry in the matrix A times B plus C? Well, that is a product of two matrices. Because of that, I will use the row column form. So I take the row, the ith row of A, that's capital A sub I, and I take the jth column of B plus C, that's B sub J plus C sub J. I think of them as vectors, and I just take the dot product. That's it. That will then be the ith jth entry of that product. But now it's a dot product. Because of that, we have all these cool things about dot products. Ignoring the way they look and just treating them as vectors only, we know that the dot product distributes through the sum. So we get that. But this one right here is a product of a row and a column. So you think of them now as this row and column vectors again. That means that is a ith jth entry of a certain matrix product. The same can be true here. That is a row times a column. So then that is the ith jth entry of a certain matrix product. Those matrix products are A times B and A times C. So I take the ith jth entry of the matrix A, B. I take the ith jth entry of AC, and it's equal to the dot product you have above. But then that, if you take the ith jth entries of two matrices and add them together, you get the ith jth entry of their sum. That's the definition of matrix sum. So then this would have to equal the ith jth entry of the matrix A times B plus A times C. So I just showed you that the two matrices I gave you above in the equation not only are the same size, but they have corresponding entries that are equal. Kind of nice, huh? That's kind of nice. Now, you have to be careful. So while you can use those properties, the few properties I gave you for matrix multiplication, associativity, distribution, but don't change the order, reassociation with scalar multiplication, and then the identity matrix times the matrix. Those are the properties that are true. Practically everything else isn't. Practically everything else you would like to be true is now not true because this first thing is just not true. Because this is not true in general. A times B is not in general equal to B times A. That means then this one's not true actually in general. This one's not true in general actually. This one's not true in general actually. To show you why, I'm going to take A plus B squared, and I'll show you what it actually equals. It is not that in general, because this is not in general true. So then A plus B squared is A plus B times A plus B. Think of it as a matrix being multiplied into a sum. So that is by definition is A times A, well, not by definition, by the property I gave you, it'd be A times A plus B times A plus B. Notice I did not change the order of the symbols. But then again, by distribution, this would be A times A plus A times B. Again, not changing the order of the symbols, plus B times A plus B times B. But assuming that you can actually square it, assuming the sizes are correct so the notation works, this can be written as A squared plus A times B plus B times A plus B squared. And notice that's not this. The problem is right here now. Because A times B and B times A may not be the same thing. So they're not like terms. So it's not just 2 times A times B. That's the same problem occurs with all the others. So A minus B times A plus B is not A squared minus B squared. Not when you have matrices. If you have A times B to an integer power, it's not equal to A to the integer power times B to the integer power. Again, because of that first property, because you can't change the order, all of these now are not true. Not in general. They might be true for particular matrices, but in general, they're not true. And I think that's enough for that part of the video.